So let's look at examples, some examples, how we use, given a current, okay, how we use the Biot-Savart's law plus the linear superposition to figure out the magnetic field created by this current distribution. Okay. Now, of course, the simplest case for the electrical case was just a point charge or maybe several point charges added together. But in the case of magnetic field, we need a current. A current, you cannot think of it as a point, right? That doesn't make any sense. It has to flow in a wire. And the simplest possible geometrical shape of a wire is a straight wire. Okay, it's a straight wire. Now, let's first consider the case when the straight wire is infinitely long. It is infinitely long. Okay, it's infinitely long and it's straight. We wish to know the magnetic field at point P. This will give us a good exercise, how to use Biot-Savart's law and integration to figure out the magnetic field of a current distribution. Alright, the idea is we're going to cut this current into small current elements, and here is a typical element ds from here to there. This is the unit vector r joining ds to the point of interest, okay, and the angle between them is theta. Let's first find then dB, the magnetic field produced by this current element, and then we're going to integrate over to get the sum over dB, so we get the total magnetic field produced by the entire wire. Now, first of all, what is the direction of the magnetic field produced by this little current element? Well, it is dB cross r, right? dB is this vector, r is that vector. So dB cross r, what do you get? You get a current, you get a magnetic field flowing, pointing directly into the paper, right? Pointing into the paper. And that, in fact, is the same for all current elements for the entire segment. So that's good news. That means every one of these dBs will point in the same direction, okay, into the paper. So you don't have to add them like vectors, just sum over their magnitudes. And of course, the total B also points into the paper. So all we have to know is to find the magnitude of dB. What's dB? What's the magnitude of dB? What's that equal to? Well, dB equals to Biot-Savart's law, mu naught over 4 pi, right? That's the constant. I ds cross r over r squared. And let me find the magnitude, okay? The magnitude. Because I only have to add the magnitudes up. Okay, let's see what we get. Mu naught over 4 pi, I. What's ds cross r? Okay, ds is from here to there. Okay, r is a unit vector, so this is just ds times the magnitude of r, which is unit vector r, which is 1, and times what? Times sine theta, right? Sine theta. And you divide this by what? By r squared. Okay, now the next step, of course, is to integrate over dB, the magnitude of dB, to get a total magnetic field. Before we can start integration, we first have to clean up this expression a little bit. We only want to integrate over one variable. But look at how many things can change as you move along the wire. ds, that's a variable. Theta is a variable. Even r is a variable. Okay, r is this between here and there. That's a variable. So we're going to clean things up a little bit. Let me express all three variables into one. Okay, we can express in terms of r, we can express in terms of theta, whatever. Now, what I'm going to do here is I'm going to rewrite, I'm going to make a choice. I'm going to rewrite ds and r, both of them, as a function of theta, okay, and some other constants. So then I can integrate over theta. Let's see how I can do that. First of all, what is r? I would express this distance r in terms of theta and a constant. That constant is a, the distance between the point of interest and the wire. Okay, you know a over r equals what? Sine theta, right? So a over r equals sine theta. So 1 over r equals sine theta over a, which I'm going to plug in here. Okay, that's one thing. Another thing is, what about ds? Okay, what about ds? Well, ds is this length from here to there. It is really the infinitesimal value, infinitesimal increment of this distance, which I call x. Okay, the question is, given a and given theta, what is x? Okay, what is x? Well, isn't it true that x over a should be cotangent theta, right? Or a over x equals tangent theta. Okay, so x over a equals cotangent theta. I'm looking for the infinitesimal change in x, and that will be ds. Alright, so what I'm going to have to do is to differentiate both sides. okay, to differentiate both sides so that I'm going to get dx in terms of d theta. And that dx, the magnitude of ds, is just the magnitude of ds. They're the same thing. Okay, so let's do that. Okay, so we're going to write dx equals a times d cotangent theta, right? Okay, and then you know what d cotangent theta is. It is a times what? Cosecant theta d theta squared, or cosecant theta squared. Cosecant really is 1 over what? 1 over sine, okay? If you remember that, 1 over sine. So this is a over sine theta squared, and then d theta. Okay, now plug both this and that into here, and let's look at what dB turns out to be. dB is now equal to mu naught I over 4 pi. Okay, now ds. ds is just the same magnitude of dx, so I'm going to copy that, okay, which is a over sine theta squared d theta. Okay, that's ds. And then there is another sine theta copied from here. And then there's 1 over r squared. Okay, move the a over down here. So 1 over r equals sine theta over a. So 1 over r squared is then sine theta squared over a squared, right? Okay, you see, sine theta squared, they cancel out nicely. You only have 1 sine theta left. And so you clean this up a little bit. This is mu naught I over 4 pi. There's an a, there's a squared, so it's a. There's 1 a left. Sine theta d theta. Gee, look at how simple that is. Just sine theta d theta. Okay, now, so this dB, let's integrate. So b equals to the integral over dB. Okay, you just integrate. Right? I took all the constants out. The only thing left before we can finish the integration is to determine the upper and lower limits. Okay, the y is infinite long. So imagine this way down there. What do you think that angle theta is equal to? When this element, this current element, is located way down there? 0, right? It is 0. Now, and then imagine the other end goes all the way to the other end. What do you think that angle is equal to? Well, the angle is between the wire and the radius and that vector r, right? And that vector r. So way up there, okay, way up there, the wire goes this way, the r vector goes that way. So from the wire to the radius r, I mean to the unit vector r, what do you get? You get an angle that's almost what? 180 degrees. So that's pi. Okay, that's pi. So all you have to do is to integrate between 0 to pi for sine theta, and what you get is a negative cosine theta, which when you take the upper and lower limits, you get 2. Okay, so this integral equals 2. We've done that before, and of course certainly in your math class as well. So that's mu naught I over what? 2 pi a. Quite a simple expression, even though we did have to do some integration to get to this point. But the final expression is quite simple. It is quite simple. Now take a look at this. Is our first example in how to calculate b. Okay, take a look at the result that we got. No matter what the current distribution is, the b field that you get eventually will have to have the right dimension. Okay, have to have the right dimension. Look at the dimensionally. What do you get? There is always a mu naught, because that's in Biot-Savart's law. So it's always mu times what? Times there's a current. You see, there's also always a current, and you have to divide it by some sort of length. Okay, in this case, a is the only length in the problem. So as far as the magnitude, the dimension is concerned, make sure that your final result for b should be the product of mu naught times some sort of current divided by some sort of length times some maybe numerical constant, pi or whatever. This has to be the case. Okay, and another thing is, you can take, if you take a look at the expression, it's kind of similar to what we got for the electric field of an infinitely long rod with uniform charge distribution, right? Remember how we got that? Well, we integrated first in chapter 23, and then in chapter 24, what did we do? We repeated that problem with a new method that was Gauss's law, right? In Gauss's law, it turned out this method would give you a much easier solution, but no matter what you did, the answer was the same, and the answer at that time was 1 over 2 pi epsilon naught a and here is instead of I, you have lambda. Okay? You have lambda. So that was E. Look at these two expressions. Look at how similar they are. Okay, there is a 1 over 2 pi. There is a 1 over 2 pi. Now, something you want to pay attention to. Here you got 1 over epsilon naught, and here you got mu naught. Numerator, denominator. Now, how come this guy is in the numerator? That one is in the that one is the numerator. This one is the denominator. Well, that is purely again due to convention, because Ke was defined as 1 over 4 pi epsilon naught. You see how epsilon naught is in the numerator, is in the denominator, and then but Km on the other hand is mu naught over 4 pi. They both have a 1 over 4 pi in it, but we put mu naught here in the numerator and epsilon naught in the denominator. So naturally they go to different position. If this guy is the numerator, then that one must be in the denominator. Okay, so if you look at the analogy between the E field and B field, okay, every time you see an 1 over epsilon naught in the case of electric field, you should replace it by mu naught, not 1 over mu naught. Okay, that's how the analogy goes. And both behave like 1 over a. That's how they depend on the distance, 1 over a. And here the source of the electric field, of course, is a charge density. Here the source of the magnetic field is a current. So look at the analogy between the two. From this analogy, you might start to wonder, is it possible for me to redo this problem, redo this magnetic problem, just as I did with Gauss's law, so that I can use a new method, just like Gauss's law, but in the case of magnetic field, to simplify this calculation. So you didn't really have to do this or this integral, and you get this result by choosing a certain Gaussian surface or whatever analogous to it. Is it possible? Well, to do so, we must introduce something analogous to Gauss's law. So we went from Coulomb's law to Gauss's law, right? We can also go from the Biot-Savart's law, which is analogous to Coulomb's law, to something new, something that is analogous to what? To Gauss's law, okay? And it turns out, yes, this can be done. In fact, we're going to do it later in this chapter. But let's make sure we know how to calculate this, if we have to. Okay, if we have to start from Biot-Savart's law, we know how to do that. All right. So let's look at our second example. This is more interesting. What we have here, okay, is a semi-infinitely long current, straight current, and another semi-infinitely long current. Okay, they're bent into a 90-degree angle like that, and the bending does not take place abruptly. Rather, it takes place in the form of a circular arc. Okay, it covers a quarter of a circle of radius r, and we want to know what is the magnetic field at the point P. Okay, which is the center of that arc, of that circular loop. Okay, the center of that circular loop of radius r. How we do that? Now, we learned in the previous problem how to find the magnetic field of an infinitely long loop, infinitely long wire. How do we apply that knowledge plus something new to solve this problem? Well, first of all, you know, we can think of the magnetic field as a sum of three fields. One produced by this guy, and then another one produced by this guy, and another one produced by the circular loop. Okay, and let's look at them one by one. First of all, this one from here to there. Okay, we call the field produced by this part of the wire as B1. What is B1 equal to? Well, we never calculated B1, but in the previous problem we did something similar. We calculated the B field of an infinitely long wire extending all the way to infinity. What we have here is a semi-infinitely long wire. It ends up here, okay, but the other end is infinity, so we call it semi-infinite long wire. What's the difference between the B field of an infinite wire and a semi-infinite wire? Well, suppose I have an infinite wire, okay, infinite wire, and then let's look at a point P here. Now, this is one single infinite long wire, but I can mentally divide it into two parts, okay? Here's one semi-infinite one, here's another semi-infinite one, each carrying the same exact current. Okay, this have produced a certain B field here, that have also produced a certain B field here. What can you say about these two B fields? Well, guess what? They produce an equal amount of B field at this point. Does that make sense? Okay, look at the direction. Okay, this is ds, this is r cross ds. Don't you point inwards? Same thing here. This is ds, and r is like the r cross ds. Same, I mean ds cross r is also inward. Okay, either way they produce a B field inward, and they have the same current, same geometry, and both are semi-infinite long, have the same distance, and therefore they should produce an equal amount of B field. Now we do know the total B field at this point. We already did that. That was mu naught I over 2 pi a, if this distance is a, right? So how much does each produce? This half and that half. That would be mu naught I over 4 pi a, right? Half of that, right? So that's exactly what we need to know here. This is a semi-infinitely long wire, and so how much B field does it produce at this point due to this semi-infinite long wire? It is equal to, okay, I'm going to write down B1 now. B1 equals to what? Mu naught I over 4 pi r. Okay, r is the distance instead of a. What is the direction of that B field? Okay, suppose there is a current element here. That's ds. ds cross r, right? R is a unit vector pointing from here to there. ds cross r inward, okay, into the paper. That is the magnitude and direction is into the paper. Similarly, you look at the B field produced by that guy, also in semi-infinite long wire. You would get the same exact value. Okay, so we call it B2. B2 is mu naught I over 4 pi r as well. And what about the direction? There is a ds and there is r, so ds cross r, it's also into the paper. So this semi-infinite wire and that semi-infinite wire, they produce the exact same value of B field, both same magnitude and same direction at this point. So you add them together, just add the numbers together. That's all you have to do to sum them up. Okay, so we can see the only thing we have to do, the only thing that's left, is to figure out the contribution from the quarter circle loop. That's all you have to do. Okay, so let's do that. Let's do that. Again, we have to divide it into infinitesimally small pieces. Let's look at a piece from here to there. Okay, and then this will be ds, right? This will be ds, and r, the unit vector, will be along that direction. What is ds cross r? ds cross r. You see, it's also inward. Okay, so even the quarter circle loop produced the B field exactly in the same direction as B1 and B2. So that is good news. dB1, dB3, we call this dB3. Okay, you only have to worry about the magnitude, because then all these magnitudes can be summed together since they point, all the vectors point in the same direction. What is that equal to? Forget about, okay, I forgot about mu naught over 4 pi. I have to write that first. Mu naught over 4 pi. I ds, what's ds? ds is the length from here to there. Okay. Times the unit vector r times the angle between ds and r, which is what? 90 degrees, right? ds and r. So that's sine of the angle between, that's just 1. So just I ds, that's it, times 1 times 1. Divided by what? That's distance squared, and that's just r squared. That's it. Okay, that's it. Now, that is only dB3, however. I have to integrate to get B3. B3. You notice, again, I only integrated over the magnitude. I did not even bother to write the vector sign because all the dBs point in the same direction. I just add their magnitudes up. Let's look at how we add them up. Okay. Mu naught over 4 pi is a constant. What about I? Well, I, of course, is also constant. It never changes from here to there. Even r squared is a constant. Okay, that is the beauty of this geometry. It's just part of a circle. So r is a constant. Take everything out. Mu naught I over 4 pi r squared. The only thing left is ds. The only thing left is ds. Integration of a ds. That means I'm adding all the lengths up from here to there. You get just a quarter of a circle. Circumference divided by 4, right? So what is that? That will be pi r over 2. That's it. Okay, so this is pi r over 2. You work that out, you find it's mu naught I, and then what do you have? You get r. Okay, there's a 4 pi here, and there's a pi over 2. So overall, what do you get? You get 8. Mu naught I over 8r. That's it. That is B3. Okay, now again, B1, B2, B3, they all point in exact same direction into the paper. So B at point P is simply the sum of B1 plus B2 plus B3. Okay? And then just add them together. This plus this, that is mu naught I over 2 pi r. Just add them together, and then add, don't forget that term, mu naught I over 8 r. Okay, that is the magnetic field at point P. Magnitude, direction is into the paper. And you notice that it's got a correct dimension, mu naught times the current divided by length, and the only length in question, of course, is r. Okay, of course there is some numerical constant, like 1 over 2 pi, like 1 over 8, that sort of thing. But overall the dimension is correct. So that example 2, the reason why we put that example in is because I want to show you how to break the source into several segments if necessary and add them up later.